So yeah, that. Yes, usually when that happens, that's like I just got a text stamp from my mother. That's how I know it's my mom, when I get 6 text messages in 2 seconds. Anyway, so yeah, we were just talking about the homework and how that's going to work. It's due, in case you didn't notice, at the beginning of class Thursday. So for those of you who haven't looked at it, or for those of you who have looked at it but not done it, like there's a handful of people that have an attempt, but it's an attempt in progress, which means you looked at it, might have saved 1 or 2 things, but didn't submit it. So that's fine too. But make sure you go back in and submit it and finish it before class on Thursday, because the online system will grade whatever you have as of that time.
You mean next Thursday?
No, I mean in 2 days.
But on the syllabus it said next Thursday.
Assigned first week of class, due, the first one should be due the second week. So the first assignment you have was assigned on Thursday of last week, is due Thursday of this week. Thursday of this week you'll get another one, due Thursday of next week. And that's why you have 7 homework assignments and the 8th one is free. Because I couldn't give you a homework assignment the Thursday before the semester started due the second day of class. Make sense?
Yeah.
That, you might be right. I may have worded that wrong in the syllabus.
Did you add the second one yet?
No.
The first one said it was due on the 17th, so.
Exactly.
Let's go look.
It really says that.
It should be due.
At least in the homework, please.
Yeah.
No, you're not, because I printed that off.
Yeah.
And I was like,
And was that what the syllabus said, or is that just what it said on D2L?
On D2O.
Yeah.
What the heck is that keyboard? Let's fix that now. Because we are in today, the second week of course, right?
Yeah.
So, right. Let me check.
It confused me too, because
Right.
I thought you said it was due this week, but it said it was due next week.
Right, which would give you lots of time to not worry. Yeah, it totally says due on May 17th. You're right.
mm-hmm.
Okay, we're going to change that. Somehow, to last March. Yeah.
I mean, that's fine. I just.
That's
No,
why I
I'm
was
glad.
like,
You
No.
probably like assigned like chapter 6 on there, and it was kind of like weird. So it was like, well, after you do the exam, turn this in.
Has a due date. There we go.
Okay.
And yeah, even the end date, I was just totally off my rocker, evidently, when I was making the first one. Because I had the end date as the 17th as well. So, has everyone 1, 2, 3, 4, 5, 6, 7, 8, 9, 4, 5, 6, 7, 8. Great. Okay. So, so there we go. And I will need to send out a email to everybody, just unless everybody actually shows up, to make sure that we're all on the same page. Because I don't want somebody taking an extra week and then suddenly realizing, hey, where'd the first homework go? Yeah, that's my bad. We'll turn that back on. So yeah, from now on, for the rest of the 7 weeks we have left, right? It'll be homework due on Thursday. New homework popping up Friday morning, which will be due the following Thursday. So every homework you'll have about a week to do, which should give you plenty of time to take a peek, check with friends in class, right? Work on a few things. The test will open up Friday morning, so that means every other week there will be a test that opens at the same time as the homework. They will be named completely differently. But the exams, which will be called exams, will also open up on a Friday morning. By way of example, the first exam will be opening up when? This Friday morning, right? At about 8 o'clock. And it'll be open until when? Sunday at 11:55. Midnight, but I can't do midnight because that's technically Monday, right? So that's why it's 11:59 right? So you'll have until midnight-ish on Sunday to take the exam. Now, I have set up about 3/4 of your exam, so we're pretty good idea what's going to be on it. By way of example, Chapter 2, the questions from Chapter 2, there will be, I'm going to assume 12 of them, which means that you'll get 12 questions per chapter on your individual exams. So there'll be 12, so 48 questions total. You'll have 2 hours to take the exam, but by way of example, the Chapter 2 questions, 75% of them are math. Now, some of the math is really simple. Some of the math is a little bit more complex, right? Chapter 3 is about 50% math and 50% conceptual. So this is why I am glad that I went with the 2-hour time point, I guess, for our exams here, just because that gives you a little bit more time. Is that door unlocked? Are they coming in?
Yeah, they're coming in.
Okay, good. I was just making sure. So that should give you enough time, I hope, to still be able to, do the math on the things that require math, answer the conceptual questions that you are relatively certain of, look up the ones that you're not so certain of, but do be sure to budget your time. I can say this from my personal experience, with 90-minute time frames from introductory biology classes, the vast majority of students were finished on average in 26 minutes. But biology tests also require very little math. So, I anticipate that a 2-hour window should still be around that sweet spot. We'll have to, if there's a significant impact from that, we'll see. I can adjust things moving forward. Any question?
Will we know if we got questions wrong on the homework? Will we know which ones? Because working through them, I was like, I think I know what I'm doing, but I don't want to.
I don't think it's graded question by question. I think it's graded when you're done and submit it.
Or no, I'm talking about the homework.
Yes, even the homework.
But when you go back through, will we?
Yes, I'll give you. Well, there's one person that I've looked at. I don't remember who, but I just went in to look to see because I was waiting for somebody to finish homework, and I went in and checked, and there were 2 questions that I gave points back for because of mistakes exactly like that, the 450 versus 450G, right? So I did put in feedback for that attempt. I went ahead and put a little note that said I've looked at yours. So.
But it won't say you got question number 3 wrong, so that we can go back and look at it.
I honestly don't know.
When you get something wrong, it'll show you at the very end. It will say 0 out of so many points.
Right, but so I already submitted mine, and it started out saying that I only got so many out of 12 correct because he has to go back in.
Right.
And so now when he goes back in.
You can't view it until all the quizzes are submitted. Because otherwise one of you could take a quiz and see which ones are wrong. And
so once everyone is submitted and is final and the grades are finalized, you should be able to presumably then go back and look at the questions.
Okay.
And it's not real intuitive to find it. You have to click on the attempt and then
that should
it views something, but it's not what you expect.
Okay.
So there might be a little bit of a learning curve with respect to D2L. I am invested in figuring that out because I do think you should be able to go back and look at that, and so we can figure that out once everyone finishes the first homework. So since everyone should have it done by Thursday, I'll try and go in and get everybody's graded that hasn't done. So if everybody can try and maybe get it done, by tomorrow evening, then I can try and make sure to grade everybody's by tomorrow evening so that we can actually look at it Thursday during class. Okay. That being said, Chapter 6 is ginormous, so we won't spend a lot of time on it, but we can spend enough time to make sure that we all know how to go back and do that. Question?
So Chapter 6 is going to be on this exam?
Yes, it'll be 2, 3, 4, and 6. We're skipping 5, which is why Chapter 5 notes are A, not available online, B, not mentioned in the syllabus. And that is because Chapter 5 is nuclear chemistry, so it's radiation, isotopes. We're going to have a little bit of isotopes in chapter 4, but it's nuclear imaging, MRIs, that type of stuff, which is still useful, but not a part of the main learning objectives for Introduction to Chemistry. So, if you're curious, I highly advise that you read that chapter in your book, but I will not be quizzing you. Any other questions before we get started on chapter 4 today? All right. Okay. All right. Let's start talking about some actual chemistry instead of, well, that's not fair. Chapter 3 had some actual chemistry in it too. Elements. Learning goal for 4.1, given the name of an element, write its correct symbol. From the symbol, write the correct name. There's some implication there about memorization, which of course in open note homework and open note exams is not quite so much true. I can remember the day when one might be afraid that in Chem 1, if not Chem 1, at least in Chem 2, you'd have to memorize that whole table over there. Because you just needed to know this stuff. Well, back in the day, maybe that was really never true, because you could always just look this stuff up. But, you know, on exams at a minimum, you couldn't. Nice chemistry professors might, give you a handout that was the periodic table on an exam, perhaps. I will not be doing that because you all have a book, right? I will point out that the test questions by way of example from chapters 2 and 3 for conversions, I'm not going to be giving you the conversions that you need in the question, which you would get if it was a pen and paper in front of you test, right? And that is because you also have access to your book and some conveniently markable tables where those things might be collated into easily accessible groups of information, right? So, just so you know, that's going to work. All right. So, what is an element? We've already talked about it. A pure substance. All of reality as we know it, at least with respect to mass, is made up of the, 111, 118 written in here, known elements, the vast majority of which, or I should say a small proportion of which really don't exist unless we make them. Some of them are on that periodic table and are known, but they are only known because we made them. And that is because of aspects that we'll be learning about today, that the nucleus of those atoms are unstable. And so, if those atoms ever did exist in nature, they existed for only a very brief period of time before they broke down into smaller nuclei, which makes them different atoms of different elements, right? But an element itself is a pure substance with the same arrangement of protons, which we'll get to in a little bit. It cannot be broken down into simpler substances, but it can be broken down into smaller parts. That is to say that the subatomic particles that we'll be talking about later, i.e. protons, neutrons, and electrons, all of you should be familiar, at least with those three things, right? Those three things are exactly the same things that make up every element on that periodic table, therefore make up every atom, that makes up every molecule, that makes up every portion of your body. And yet, just like previously when we talked about chemistry, the thing that makes different chemicals different is because of the order, number, and arrangement of the atoms found within them. The thing that makes those atoms different is because of the order, number, and arrangement of protons, neutrons, and electrons within them. So, all carbon atoms, if you'll follow the red dot on the periodic table over there, all carbon atoms have 6 protons in their nucleus. If they were to have less than 6 protons, like 5, they wouldn't be carbon. If they were to have more than 6, they wouldn't be carbon. 6 protons makes you carbon. Now, carbon itself has more than simply 6 protons in the nucleus, and we'll talk about what those other things are as we progress through this chapter. But everything that is carbon has 6 protons and therefore cannot be subdivided or broken down into simpler substances. We can take that carbon and break it down into protons and neutrons, at least conceptually. Doing so physically is a much harder thing and has a lot more to do with chapter 5 and 4. Sulfur, by way of example, is an element. Here is a powdered collection of some pure sulfur. Here's an example of some elements. Uranium, abbreviation U, name came from the planet Uranus. Titanium, from Titans of mythology. Chlorine, from chloros, or greenish yellow, which is from a Greek source. Iodine, from a Greek source of violet. So there's all sorts of nifty things. I'm not even going to try it. I'm not even going to try it really. Well, I just tried it like 4 times and failed probably. Abbreviation TS. So there's americunium, over there. So where we name things, who names them, where we find them, as we discover them, we get to give them nifty little names. So that's where things like Americunium come from, is because, hey, we're in America and we made something and stuff. You know, and then we let Europe build a Hadron Collider, and we just kind of took all of our cool toys and handed them to Europe and said, we don't care anymore. But that's a political talk, not a chemical talk, so we can just leave that in there. Once again, this type of stuff you can look up. Obviously, some of the most common and especially biologically relevant atoms, hopefully, if you don't already have them, by the time we're done with this class, you'll just kind of have them by rote memorization. For example, what is the chemical abbreviation for carbon? Oxygen? Hydrogen? H, right? So a lot of the common and biologically relevant atoms have pretty easily rememberable things, but then there's also some odd ones, like, for example, we come up with something slightly odd like mercury. What's the abbreviation for mercury? Anybody know?
Maybe.
Hg.
What is
So like what? So some of them are not so common, right? Some. Remember, CO here is the chemical abbreviation for cobalt. You know that it is one atom because it is a capital letter with a lowercase letter right next to it, right? Because we could also get CO, but because they are both capital letters, that tells you that this is not one atom, but two, the carbon and oxygen atoms, respectively. So an appreciation for what that lowercase letter means is critically important when we start dealing with these larger polyatomic combinations, molecules, right? An even larger table of common things, so that you have the names that go along with the things that are over there on the periodic table. Not to spend a lot of time there, because you can look that stuff up. Some of the sources are from Latin, like AU for gold, AG for silver. Where they come from is a neat historical component that I'm not going to spend a lot of time focusing on. Here's our mercury. It is the only metal that is liquid at room temperature. And it is also something that is very, very dangerous. Anybody know, have you guys heard of the phrase mad as a hatter? Which is conceptualized from through the looking glass. We have the Mad Hatter. It's crazy, having a tea party. Why were hatters mad? Well, because back in the day, people who made hats, they did so with a whole lot of liquid mercury. They would soak the hard material that they were working with in liquid mercury in order to soften it so that they could form it into these beautiful and intricately shaped hats. Well, that also meant that they were literally dipping their hands in large vats of liquid mercury and inhaling the vapors that were coming off of it and driving themselves batshit crazy. Because mercury is cytotoxic, neurotoxic, it does bad things to your brain. So, not good. If you work in a university like this, and work in a lab that has even any potential of becoming involved in mercury, back at MS&T when I worked there, we had this horror story of students who lived in the dorms, and one of them took an old mercury thermometer from the chemistry lab that they were working with, took it back to his room, and it broke in his room. And that tiny little volume of mercury that dripped out of that broken thermometer required them to use a special, exceptionally expensive vacuum wall off that room, and they couldn't go back into that room for 3 days while they effectively decontaminated that living space from that little drop of mercury that was now soaked into the carpet of their room. So, this is why most thermometers that you get nowadays, if they're not just digital thermometers in the first place, are not going to have mercury in them. They're going to have some other liquid that responds to temperature. Question?
If you call poison control because you broke a thermometer,
Mm-hmm.
they just tell you to get a tissue, wipe it up, and don't let any of it touch you.
Don't let any of it touch you?
Yeah.
Yeah, just grab a tissue, grab some Kleenex, wipe it up. That is a nice anecdote Because frequently, especially nowadays, like I said, if you break a thermometer, it's probably not actually a mercury thermometer, and so it's really not an issue. But it's probably one of those middle grounds where as institutions regulated by OSHA, we have to be a lot more concerned and careful and completist when it comes to how we handle chemical contaminations. We're as opposed to, you know, in your kitchen or something, maybe it's not nearly as much of an issue. A little bit of mercury isn't going to kill you. And we get, unfortunately, a surprising large amount of it from some of our foods, especially fish, can have a higher content of mercury than is healthy. There's a big, you guys heard of thimerosal? It's a preservative, or that used to be, it still is involved in some vaccines, but it's been removed from a lot of them, especially the ones that we give to children. There's a big concern over thimerosal as a preservative in vaccines as something that could be causing damage. But that is, and the idea there is because thimerosal is a chemical that does actually contain mercury. One atom of mercury among a large number of other atoms of other things. But that's scary because people know that mercury is bad for you, and so obviously anything that has mercury in it should also be bad for you, right? Well, something that we will learn when we talk later on about the nature of some of these elements. Table salt, what's that? Sodium chloride. What does sodium by itself do? If you take raw sodium and add it to water, you will get an explosion. If you take chlorine in its natural state, in its highly concentrated natural state, what would it do? Kill you. Or, well, if you breathed it in especially. It would, if you breathed it in, it would cause major problems up and including dissolving into the liquids of your lungs, turning the liquid there into acid, and therefore dissolving the inner linings of your lungs. That's what chlorine gas does. That's how people died in the trenches from chlorine gas in World War I? Yes. We had more creative ways of killing people in World War II. So, but still, bad stuff. And yet, nobody's afraid of table salt. Right? Guess what else is in thimerosal? An atom of sodium. That makes it doubly dangerous. Question?
I have a friend who's a biochem grad.
Yeah.
She won't eat sucralose
Okay.
because she insists that she can taste the chlorine and the chlorine in it. And I'm like, blows up a salt shaker at her.
Well, I assume that your friend is still human, right? Therefore, as human, she is capable of making all of the same errors in judgment that any other human is capable of doing. Let's just say. Yeah. I don't know. I'm definitely biased with respect to certain things. I'm a scientist by way of profession otherwise, so I have a certain belief, understanding, strength when it comes to scientific understanding of things. I was watching an episode of a show last night, and there were these parents who didn't want to give their kids antibiotics because they'd read that antibiotics were bad and it could cause all sorts of bad things, and just like the problem was that none of what they said was a lie. Everything that they said about what antibiotics could do is true. In the same way that if you stood out in a thunderstorm, you might be hit by lightning. It is true. And therefore, it is probably wise to not stand out in a thunderstorm. But, you know, we have ways of mitigating the risks of being hit by lightning in the same way that we have ways of mitigating the risks of taking antibiotics. And so it's just like, annoying for me. Granted, it was just a TV show, but it was a dramatization of something that annoyed the crap out of me, which is, you know, basic foundational science. Everybody should know this. Just everybody should know this. But maybe I'm biased.
My mom does the same exact thing. She's a micromolecular biologist. So everything wrong with the TV show she could find, she'll point it out.
Right, yeah.
Yeah.
Doctors have turned house into a drinking game and they get quite drunk.
Yep, yeah. I will do the same thing except with children's shows. Like when Daisy grabs balloons and then when she grabs one more balloon, she begins to fly and float away. And I'm like, okay, there's the physics of this, and my wife just tells me to shut up, and it's a kid's cartoon. Not think about it that deeply. She's right, but yeah, so there we go. All right, in the body, mercury destroys proteins. It disrupts cell function. Long-term exposure can damage the brain, the kidneys, mental retardation during development, decrease physical development and cause neurological disorders. And we can actually use blood, urine, and even hair samples to test for mercury to see how much you've been exposed to it over your lifetime. Because we don't have a good way of handling this metal. And that is because we evolved as biological organisms in a world that did not have a high amount of exposure to mercury. So we did not evolve any mechanisms to get rid of it, to handle it. So it sticks around. Here's our periodic table. Learning goal for 4.2, use the table to identify the group and period of an element and identify that as a metal, a non-metal, or a metalloid. So we have an organization of our periodic table here. We have alkali metals, alkali earth metals. This is group 1, group 2, transition elements that we're sort of skipping, unfortunately. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so we're pretty much skipping most of all of this stuff down here when it comes to getting a detailed look at them for this class, because it is an introductory class, so we're going to learn about some of the basics of going through the first few orbital shells of the periodic table, but not really get too deep into the lower orbital shells, which I find to be annoying, but I'm also going to understand we only have so much time. So here we go. 1869, Dmitry Mendeleev created the periodic table by arranging the elements in order of increasing atomic mass. Now this is actually something that I am, like, the process through which he did this is something I'm somewhat ignorant of, and it's kind of one of those things that if I was really motivated one day, I would go look up the background story on this, because every now and again I'll get a bug up my butt to find some area of scientific ignorance that I have and shoot it with as much knowledge as possible. By way of example, anybody in here know how metal detectors work? If you don't, you should look that up. It's really cool. Doesn't have anything to do with this. But, like, you know, just finding answers to these things that are science, and how does that work, and that's neat. He arranged the elements in order by increasing atomic mass, and that is how we knew that there were things that we had not yet discovered. By way of example, at the time, we discovered that guy right up there, helium. We discovered it on the sun long before we discovered it on Earth. Because we knew that there was something that should go there. Because when we arranged the atoms by order of their atomic mass, they fell into these neat little organized groups, which are the columns that you're looking at in those, on the periodic table, the periods. And so we realized that there were some gaps. There were some spaces in there. We had a 1, we had a 3, we didn't have a 2.
Are we in a helium shortage still?
So, I don't know about still, but yeah, sort of. Yeah, helium's actually not that common on Earth. It's one of the reasons why it's actually, like, more and more expensive to go buy helium just to blow up balloons for parties and stuff. Because the main reason is because for a while there, the only thing we really used helium for was to make balloons float! And then we started making these really nifty scientific tools that required helium as insulators, cooling elements. So, so there were some things that needed a lot of helium, and as we get more and more of them, more and more of the helium is going towards industry instead of children's parties. So,
He used a lot of it enough.
yeah, yes, a lot of digital helium. But it is a finite resource on Earth until we've mastered the art of atomic fusion in a controlled fashion, at which point we'll have as much of it as we reasonably want, as long as we're willing to burn through the hydrogen, which we have a lot more of. So, here we go. So here we have periodic table of elements, representative periods here. So we have 1A, 2A, 3A. You'll note there's a 3B, 4B, 5B down here in this area that we're not going to spend a lot of time in. So 1, 2, 3, 4, 5, 6, 7, and 8. Here we have our metals in dark blue. We have our metalloids in green. You'll notice pretty much everything bordering that dark line except for aluminum. And then we have our non-metals up here. Something that we'll get to later, metals have a tendency to lose, especially the closer you get to here, but they have a tendency to lose electrons when they become ionized, as opposed to non-metals have a tendency to gain electrons as they become ionized. That's a little bit out of the box, or ahead of the box, I should say, for this chapter. There we go. So, We arrange elements that have similar properties in vertical columns that we call groups. The period or the horizontal rows, top 1 through 7. So, period 1 has only 2 elements in it. H and He. So, hydrogen and helium. 2 has 8. So does 3. Now we have the groups in vertical column. All of these guys are grouped together. They have similar properties with the exception that hydrogen is a gas and lithium and everything else down below it is a metal. And we'll get to the reason why, but can someone tell me the reason why? What is it about all of these things in group 1 that give them these similar properties that they have? What is it about group 1 that, with the sort of exception of hydrogen, that gives them their similar properties?
They have a single valence electron.
Correct. They have a single valence electron. They have 1 electron. If they were to lose that 1 electron, then that would leave them with the next shell beneath it being completely full. Which doesn't mean much to some of you yet, but hopefully it will. The reason why this group 8 over here are called the noble gases is because we apply a certain meaning to the term noble as meaning, in this case, not so mean that they attempt to steal electrons or donate electrons by way of chemically bonding with anything else. The noble gases are noble because their outer shells are completely full already, and therefore they have no interest or desire, to anthropomorphize them a bit, in losing or gaining electrons in order to fill their outer shell. Their outer shell is already full. So they do not react with things. For the most part, tiny little asterisks, they do not react with things. Because the whole point of reactions for everything else is trying to fill that outer shell. By either gaining electrons or by losing electrons enough to where the unpopulated outermost shell is now empty, and therefore the one right beneath it is completely full, and now they're nice and happy and content. And by content, I mean have reached a lower energy state that is more stable than their original state. So, period 1, period 2, and 3, this is a list. This is literally just a list of everything running across from left to right. Period 1 has 2, period 2 has 8, period 3 has 8, period 4 has 18. So groups are vertical, periods are horizontal. Groups, the vertical columns. The letter A represents elements 1A to 8A. B, which is, if I back up a little bit, these guys down here, these transition elements. These transition elements are nifty in that they can do things that some of these guys out here can't do because they have all of that extra, all those extra electrons and shells to mess around with, something that we're not really going to talk about. Because the primary arrangement of what we're talking about ends at period 3. So we're not going to have time to talk about some of the nifty things that those transition elements can do, but you should be able to identify a transition element as such. Group numbers identify which vertical column they are in the periodic table. And there are 18 total as we move across. Because that weird thing on the bottom of the periodic table is something that we just don't have time to get into it. Certain groups have common names. We've already mentioned them. The alkali metals is group 1A. Group 1. We have our alkali earth metals, group 2. We have our halogens out here, group 7, and our noble gases, group 8. Transition elements are all of those gray things down there that are in that little trough, that valley of the periodic table. We don't have common names for these guys kind of here in the middle of this light blue area here, and that's because the nature of these guys changes, fundamentally changes, as we approach and cross that dark black line up on that periodic table. So we go from non-metals to metalloids to metals as we move down and to the left through those elements. And so we can't give a common name to something that has something like nitrogen as a gas up at the top, arsenic down here in the middle, and then getting even worse for something that I don't know what Bi is. This is me not memorizing the whole periodic table either. Because I can just look this up too. Here's all of that again, but just spelled out for you, right? Alkali metals, alkali earth metals, halogens, and noble gases. So let's talk about some of those alkali metals. Lithium, sodium, potassium. All from group 1. Metals, right? With the exception of hydrogen all the way at the top. Lithium, sodium, potassium are all metals at room temperature. Does that surprise anybody? When you think of sodium, what do you think of? Do you think of a metal? Do you think of a solid when you think of sodium? Probably when you think of sodium, what's the thing that comes to mind? Salt, right? Sodium chloride, which is a solid at room temperature if it's not aqueous. If it's aqueous, then we dissolve that sodium chloride into ions in an aqueous solution, in which case it is just ionic sodium floating around. The sodium that's in your body is either sequestered in individual molecules or it's floating around as independent sodium ions in your bloodstream, interstitial fluids, in the cytosol of your cells. Sodium and potassium, those two guys right there, they are responsible for a significant portion of the homeostasis of every cell of your body. And that is because every cell of your body is a tiny little battery with a 200 or so millivolt potential. Now, you wouldn't be able to do anything with a battery with a 200 millivolt charge. There's no like remote controlled car you could run with that or anything like that. But every single one of your cells arranges those sodium and potassium ions in a manner to where there is a 200 millivolt difference across the membrane. They spend a lot of the ATP, you guys familiar with ATP? Yes. A lot of the ATP that you get from burning your food, you burn a lot of that energy just to pump sodium and potassium into and out of your cells. Because that's charging the battery that a lot of other things then use. They use the charge of that battery to do other work. But that's because you're dealing with individual sodium ions. Solid, pure sodium that is not charged is a metal at room temperature. But it's a metal, and this is what I want you to appreciate. Why does sodium, this is way out of the box, way ahead of the box, but maybe you've already heard enough. Why would sodium, a metal with one electron in its outer valence shell, because it's in group 1, that means it has one outer electron. All it has to do is lose one electron, and it will have a completely full outer shell. So how bad do you think, I'm anthropomorphizing again, how bad do you think sodium wants to get rid of that electron? It's only one off from being comfortable. You ever been in an elevator that just had one too many people? Getting rid of that one electron would make it much more comfortable. And guess what? Water has a lot of oxygen in it, and oxygen just loves collecting electrons. So when you take sodium and hit it and drop a little bit of it into water, there's an explosion. Why? Because water is more than happy to rip those electrons off that sodium. Sodium is more than happy to give it, but that exchange of electrons gives off a lot of energy. Enough energy to boil water almost instantaneously. Thus, explosion. Thankfully, the sodium you have in your body has already been ionized, and therefore there's no risk of further explosions. Not that I suggest it, but there's a nifty way, and it's actually a really hard thing to do unless you work in a chemistry lab. But there's a neat way to poison someone that most people will have no idea what's wrong with them, and it can get lethal pretty quick. Just give them a whole bunch of potassium. Okay, so remember that battery I mentioned about making sure that we have very tight control about where the sodium and the potassium ions are? Yeah, spike one side of that battery, and your body doesn't know what to do. It's hard to do if you don't have access to a chemistry lab, because most of the time, the only time you're finding potassium is already ionized and combined with other things and otherwise biologically relevant. So like, here, eat a bunch of these bananas! And then you sit there and giggle while you hope that they're gonna, like, what, get the runs because they ate too many bananas? Like, that's not really that serious of a problem. It's probably an episode of House where somebody almost dies from potassium poisoning or something who's done everything else. Halogens! Let's jump to the other side of the table, shall we? This is not me endorsing that, by the way. I'm just letting you know the nifty things nifty and dangerous things. And this is the thing, like, you can walk into any chemistry lab and there's just this jug of potassium. Like, that's dangerous. But see, we know when you're working in a chemistry lab, don't drink stuff. You don't walk into a chemistry lab and go, oh, is this water? I'm thirsty. Like, you don't do that. Halogens, the opposite side. All right, so we have our halogens out here, fluorine, chlorine, bromine, iodine. I don't remember what AT is. So here's our nice group 7 out there, right? These guys are very reactive. You guys have all heard of hydrochloric acid, right? It's a strong acid. It's nasty acid. You can do nasty things with hydrochloric acid. Why? Because it has 7 electrons in its outer valence shell. What does it need in order to be super comfortable? It needs 8. So what's it got to do? Get an electron from somewhere to fill it up with 8. Go from 7 to 8. Chlorine really likes to grab electrons. Guess what likes to grab electrons even more? Once again, let's get a little bit ahead of ourselves. Why do you think chlorine, or I should say this, let me give you the answer. Chlorine right here likes to grab electrons. Bromine does too, but not as much as chlorine. Iodine does too, but not as much as bromine. Why not? What's grabbing the electrons in this case? Why would the electrons be attracted to those atoms?
The positively charged nucleus.
Right, the positively charged nucleus at the center, right? Because we're dealing with fluorine has 9 protons, chlorine has 17. So the more protons we have, you would think the more we would want to grab those electrons, yes? Except that,
Shells are further up.
right, it's also a much larger distance because we're putting shell on top of shell on top of shell. And so what's going to be the thing that wants to grab that? Yes, it only has 9 protons, but it also only has 1, well, technically 2 because it's a group 2, outer shell. So those protons are really close to where those electrons would be. Hydrofluoric acid is nasty. That will eat through glass. Halogens. Your friend. Do we need any of these for us to survive?
Iodine.
If you don't get iodine, you get gouter and you die. Do we need bromine? Gouter, goiter. Yeah? Gout. Sure.
No, gout is a deposit of uric acid in the joints.
Yeah, so it's goiter then, not gout. Is it goiter? Turkey neck. Look up turkey neck.
Oh yeah, that's not.
Yeah, no, that's not gout. Something you guys probably aren't familiar with. Because nowadays we get iodized salt. Just a smidge of iodine. What else? You actually, do they don't do it nearly as, like everything I'm trying to think of the last few times I've gotten a shot. I don't think I've actually been sterilized with iodine in a really long time. When I was a kid, every time I get a shot, then you'd always walk away with a brown patch on your skin because they wipe down that area of your skin with iodine first. Why? because pure iodine is toxic, yo. But we need a little bit of it in our diet. This, especially the thyroid, needs a little bit of it. If you don't get enough, the brain says, thyroid, you're not doing your job. You should get bigger. But if the problem is you don't have enough iodine in your diet, it doesn't matter how big your thyroid is, you're still not going to have enough of it. And the brain's just going to keep saying, get bigger because you're not doing your job. And that leads to problems, which is why most of you probably don't know what I'm talking about, because we've had iodized salt for a while after we figured out, hey, that's a good idea. Just like we also figured out, eat some oranges every now and again, and you don't get scurvy.
That's your endemic goiter.
Well, it's hard to appreciate how big that is without, like, the scale of the neck.
That's the esophagus.
Oh, that's true. Yeah. Hold that up. Anyways, yeah, we need a little bit of iodine. Need a little bit of chlorine. Do we need chlorine? Table salt, right? Need chlorine. Fluoride. We have a little bit of fluoride in our teeth. So we need a little bit of this stuff. But too much can kill you. Especially if it's in its, chlorine especially, if it's in its gaseous form, because that's nasty. But yeah, pure iodine can kill you too. Don't drink that.
Is there anything on the periodic table that?
You know, actually, that's a good question. There's a nifty, somebody did a YouTube video of this, of what would happen if you tried to make a periodic table out of even just a tiny sample of pure whatever everything that is, right? And the first couple of rows, you're like, this isn't that bad. But by the time, especially once you get into transition metals, it's like, yeah, this will kill you, and now when you try and do this, it'll explode, and now when you try and do this, you will die a horrible death from radiative damage, and now when you, so yeah, pretty much everything on here in its pure state, bad for you. Yeah, even oxygen in its pure oxygen, not that good for you. Let's just say not that good. You need it, but we should not be breathing pure oxygen for any significant length of time. Cause a problem.
I was thinking of the Spaceballs where they pop open the cans.
Yeah, pure air. There's going to be a sequel, by the way.
Really?
Spaceballs 2.
Wow.
So search for more money.
Because Rick Moranis is back in the movies, baby. It's going to happen. So we have metals located to the left down here. We have non-metals all the way up here in the yellow. We have our metalloids, which are these things that are transitioning. Forgive me for the use of the term transition, which actually describes a whole other group. Things that are, what's a good word for transitioning that's not transitioning? Things that are adjusting in properties from one major group to another.
If I can find a thermostat, does anybody mind if I make it
Less cold, more warm.
more warm?
More warm.
Just trying to avoid the cold.
Yes, you can turn it up a degree or two. I think it's right back there. It's a bit nippy. What are some characteristics of metals? Shiny solids at room temperature, such as copper, gold, silver. They are ductile, malleable, which means that they can be shaped in different ways. They are good conductors of electricity because it's just the movement of electrons. They're melted at much higher temperatures than nonmetals. And like I said, except for mercury or solids at room temperature. Nonmetals, hydrogen, carbon, nitrogen, oxygen, chlorine, sulfur. They are not particularly any of those other things. So they are not particularly shiny, ductile, or malleable. They are often very poor conductors, and they have relatively low melting points and also low densities. You know, nice gross exaggerations about whole groups of elements. That makes them incredibly accurate, right? Except for aluminum, because aluminum is a metal in its characteristics. You have the metalloids that are on that black dark zigzag line. They are kind of in between. They exhibit some of the properties of metals, some of the properties of nonmetals. They're better conductors of heat and electricity than the nonmetals, but not as good as the metals. Which is why we sometimes call them semiconductors, because we can modify them to function as either conductors or insulators. Which is very different than a superconductor. Totally different thing. So here's a nice table describing antimony. There we go. Describing a metal versus a non-metal all the way on the right, and then our word that isn't transitioning metal, right? Metalloid. Melting point down here for our metal, 962 degrees. Our metalloid, 630. Sulfur, only 113. Getting to 962 degrees Celsius is a challenge. There are ways you can do it. It's not hard, but your average kitchen will not be able to melt silver. Like your stove isn't going to do it. Getting to 630 degrees Celsius, also not an easy thing to do. Getting to 113, you can do that in your oven.
You can do antimony in your oven too. Your clean cycle goes to 800 degrees.
Does it? The clean your oven thing? There we go. 800 Fahrenheit or 800 Celsius?
Oh, good one.
Yeah, see? We could do the math and find out what that would be. But we don't need to. So, moving on. Just we can though, right? We all agree we can. We know how to do that. So, there's about 20 elements that are essential for well-being and survival of the human body. 4 of them, oxygen, carbon, hydrogen, and nitrogen, that make up 96% of our body mass. The macro minerals, as opposed to micro minerals, those are the ones that come next: calcium, potassium, phosphorus, although not in that order: calcium, phosphorus, potassium, chlorine, sulfur, sodium, magnesium. Formation of bones, teeth, heart, blood vessels, muscle contraction, nerve impulses, acid, base, electrical potential across your neurons, all sorts of nifty things, so we need all of those too. By the way, did you know that if you listed out the most common elements in the universe, outside of silica, which we're not going to have time to talk about why that doesn't matter, but if you listed out the most common elements in the universe, the order of the frequency that you find them is the same order of the frequency that you find them in your body. Metaphorically, this should not be a surprise, because what did we build houses out of when we landed on the east coast of the US, in that large forested area of the US? What did we build houses out of? Trees, wood, right? But when we moved into the Central Plains, where there was no wood, what did we build houses out of? Literally dirt. We built houses out of what was there to build from. So, is it surprising that life is built out of what was there to build it from? Here's the next nifty thing. There's also ahead and outside of the box for this. Where do these atoms come from? Does anybody know?
God. I'm gonna say, because people are made of dirt too. Passion and sadness.
No, dirt is made of atoms. What is the natural process that gives rise to all of the elements that you find in your body? There is one and only one place that we are aware of where you can create carbon, nitrogen, oxygen, chlorine, sodium.
So,
The heart of a star. Actually, not the heart, the outer layers of a star. Stars take hydrogen and fuse it into these heavier elements. Literally, the heart of every carbon atom in your body was born in the outer layer of a star through the fusion of multiple hydrogens into heliums, multiple heliums into carbon.
I know.
If you would like to donate credit, feel free. What this means is that every element up to iron was created in a star. Every element heavier than iron was created when that star died. So where does the carbon that you use every day to survive come from? From a star.
What
Means we are
makes
all.
that cut off?
What's that?
What makes that cut off at iron?
The heat of it's the thermodynamics of fusion versus fission. When you start fusing atoms heavier than iron, it takes more energy to do so than you get out of the formation of that new nucleus. Which is why when stars run out of fuel lighter than iron, they start trying to fuse iron and go through a very, very quick death spiral that ends in a big explosion that we call a supernova. But that's astrophysics, not chemistry. So, I like to point that out though, because as Carl Sagan said, we are all just stardust. Every atom in your body came from a star. Just like the atoms in everything else that you ever see or interact with. It's kind of neat. Atoms, or elements I should say, and this is the quantity by weight and the function that you find them in the body. Oxygen, carbon, hydrogen, and nitrogen. 39 kilograms of oxygen, 11 kilograms of carbon. I thought that we're organic organisms and life is made from organic stuff, and so why isn't carbon the heaviest, most predominant thing? Good question. Yes, life is made from organic, therefore carbon-based molecules, but what is the actually majority of your body? By weight? Water. Which does not have carbon, but it does have oxygen. So the majority of your weight overall is oxygen, both in the building block of biomolecules, yes, but predominantly water. Carbon's next down, 11 kilograms. Your biomolecules, hydrogen in both water and also a lot of your biomolecules, nitrogen, primary component in proteins and nucleic acids. And then we get down into these things. Calcium, technically 1 kilogram, right? 1,000 grams is 1 kilogram, right? But these are your macronutrients. You need a little bit of iodine, but evidently a lot less than 36 grams, right? It's not on this today. So this is the list of the primary components. The typical 60 kilogram adult, that's what these are representative weights of. Just to give you an idea. There's a list out there, I don't remember who maintains it, curates it, but it's the average value of human life. Not from an ethical standpoint, but just from a, how much would it take to buy the raw materials? And it's somewhere around like $3 to just buy this much of all of these things. Now, I would be the first to tell you that that is a false equivalency. Like, person, piles of dust of things, and some gas. Like, not the same thing. In the same way that all the parts it takes to make a car does not have the same inherent value as a functional car that's all put together that you can drive down the road, right? The sum can be considered to be greater, or the whole can be considered to be greater than the sum of its parts. But yeah, it's like a few bucks. Used to be more. We're better at making this stuff. But, inflation. Microminerals or trace elements. Mostly these guys are done in period 4, silica in period 3, molybdenum and iodine in period 5. Very, very small amounts, less than 100 milligrams. Some of them less than 100 milligrams. Microminerals. We need a little bit. And the vast majority of anything else, if you get some of it in you, you're probably dead. Have fun. Iron, silicon, zinc, copper, manganese, iodine, molybdenum, arsenic, chromium, cobalt, selenium, and vanadium. Cobalt! Why do we need that? Well, that's right here. It's a component of vitamin B12. Which you need for your red blood cells. Just a little bit. Why do we need iodine? Need for proper thyroid function. The hormones that your thyroid makes need 1 atom of iodine each. Why do we need iron? Rust. Because our blood is red. Here's all of those things highlighted for you. You get too low on this periodic table and you start looking at bad stuff. Gold is toxic at high enough levels. You can buy hamburgers where they have lined your hamburger with gold leaf. Like they've taken this ultra thin layer of gold and they've put it in your hamburger. Goldschlager, I don't know if it still has it, but like that was its thing, whereas it's this alcoholic drink and it's got little tiny little fragments of gold leaf in it, so it's like, you're drinking gold, baby. It's like all that really does is make you have some really valuable poo. Because we don't digest it. Like it doesn't, but inject like gold in solution, and it gets all some bad stuff. There was an episode of House about that.
Do you know that the gold broken down into a solution is actually purple?
There are a lot of things actually that are really neat. We're going to talk about some of the reasons why some of that color stuff happened in this chapter or chapter 6. Man.
There's a lot of gold in base products too.
You know what?
Facial products, makeup.
Oh, really?
You know, like face washes and stuff like that. I have this scrub that you scrub it with the gold face wash and all your like dirty skin will come off.
So it exfoliates?
Yeah.
Exfoliates as it refreshes. Don't ask me why I know these things. I just pay attention to commercials. Let's talk about the atom. On the subject of gold atoms, here we have them magnified by 16 million times by scanning electron microscope. Don't you just love the detail there? So let's describe the electrical charge location. We're at 6:30. We're good for keep going, right? We don't need a break after an hour? Are we good? Keep going, keep going, keep going. Power through. All right. Here's an aluminum sheet, aluminum foil. Atoms, we already know, the smallest particle of an element that determines the chemical properties. The atom itself, the organization of those atoms determine the chemical properties of the compounds that they make up. Dalton's atomic theory. Here's it. Ooh, love this. The idea of atoms did not become scientific theory until 1808. What's the word that's not anywhere on this slide that would cause me to say things like this? Fact. Everything you're learning in this class is based on our understanding of atomic theory, which is, I should point out, to underline and highlight and gold star on both sides, is just a theory. Because when it comes to scientific understanding, I want you to appreciate something. It's somewhat out of the purview of this course, but just in general, if you go back to chapter 1, there is nothing in science that is more powerful than just a theory. What about laws? Good question. Theories encompass laws because laws require mathematical evaluation. One of my favorite things to argue, I'm going to put air quotes around favorite, things to argue with certain types of people are how something or other is just a theory. Coming from a biology background, you might be able to appreciate which theory I'm perhaps talking about. I've mentioned it multiple times. It's still just a theory too, evolution. Just like atomic theory is just a theory. But the difference there is because of the line between scientific understanding discussion and colloquial discussion, lay discussion. There are things like facts, right? Because you have these arguments with this, well, it's not fact yet, and the response to that is, a fact is actually the least useful thing. It's at the bottom. We start with facts, observations, facts, and then we build hypotheses and theories in order to explain why those facts happen the way they do. It's all just a theory. John Dalton developed atomic theory proposing that these atoms, these small, otherwise No longer divisible units were responsible for the combinations of elements in compounds. This theory made all those people who were trying to convert lead into gold really sad. Alchemists, yes, thank you. I was like reaching for it, didn't quite have it. Made alchemists really sad. They kept trying. So far, atomic theory and chemistry is winning. Here are the foundations of what we can now use to apply our understanding of what atomic theory means. All matter is made up of tiny particles called atoms. We've actually gone further than this to define what the subatomic particles are and even what the sub-subatomic particles are. We're not going to get anywhere near those guys in this class. All atoms of a given element are identical to one another and from different atoms of other elements. You could put a tiny little gold star next to identical from one another because we do know that there are some differences in the number of neutrons, but that does not change the properties of that atom beyond their radiostability. Atoms of two or more different elements can combine to form a compound. A particular compound is always made up of the same kinds of atoms and the same number of each kind. Water is different than hydrogen peroxide. No one would argue otherwise, right? Even though they are both made up of hydrogen and oxygen, they are made up of a different order and combination of those two, and therefore they have different properties. But hydrogen peroxide will always be H2O2. 4. Chemical reaction involves the rearrangement, separation, or combination of atoms. They are never created or destroyed in a chemical reaction. Can we create or destroy atoms? Yes. Nuclear bombs destroy atoms. And one could argue create lots of smaller ones. Suns destroy atoms by fusing them together, but this is sort of splitting hairs because it's still not destroying the things that make up the atoms. When suns fuse hydrogen into helium, they're not destroying helium atoms as much as just pushing them together to form helium atoms. It's like taking two pieces of wood and nailing it together. Did you destroy the wood, or did you just combine them? Now, we are capable of making subatomic particles. We are capable of destroying subatomic particles in things like the Hadron Collider over in Europe. We can accelerate subatomic particles fast enough and ram them into each other until they are destroyed and broken up into their subcomponent parts. But we're not going to do that in any of the chemical reactions that we're talking about here. Within chemistry, it is assumed that all mass is conserved, conservation of matter. You will never have a chemical equation where you destroy a hydrogen atom in order to power that reaction. You must account for all atoms on both sides of every equation. Because matter will never be created spontaneously and it will never be destroyed in a chemical reaction. It takes a lot of effort and really specialized equipment or very specific locations within the universe to create or destroy matter. None of which will happen, even hypothetically, in this class. By the end of the 1800s, we had gone even further to define what electricity was and to show that it was the movement of subatomic particles. We had identified protons, neutrons, and electrons. Protons and electrons first, neutrons came later. We knew, before we found the neutron, that it was there because we could identify the number of protons in the nucleus, but when we weighed them, we also knew that the atoms themselves were heavier than simply the number of protons that they had. So there had to be something there to account for that extra weight. We figured it out and named it neutrons. And our understanding of those subatomic particles is what helped us to identify that the thing that defines the chemical properties of an individual element is the number of protons in its nucleus. Carbon has 6, nitrogen has 7. Where do the charges come from? Electrical charges can be either positive or negative. We're familiar with this, right? Because we sometimes have batteries with little pluses and minuses on them. Positive charges repel, negative charges repel each other, right? But positive and negative charges are attracted to each other. Unlike charges attract, does it attract you? Anybody actually get that reference? A couple of you? Okay, good.
Not Janet Jackson. Or no, Paula Abdul.
Paula Abdul, there we go. Music video with an animated cat. Oh yeah. Anyway, so positive charges repel, negative charges repel is very similar to the north and south poles of a magnet, right? Same poles repel, opposite poles attract, right? It's more of a metaphor. It's not directly parallel in how that works, but it works, you know, as a metaphor. So, J.J. Thomson did a cathode ray experiment. Discovered that cathode rays were streams of small, negatively charged particles called electrons. And so he proposed what was called the plum pudding model of the atom, which pretty much meant that an individual atom, so these smallest units of an element, were just this hodgepodge mixture of all of the subatomic particles, randomly distributed, negative electrons and positive protons. It's this pudding here with electrons kind of just all around in the mix everywhere. And that stuck around for a little while. In 1911, Ernest Rutherford did something interesting, where he took a beam of particles, generated a beam of particles, and he shot it at a very thin foil of gold. Now, let's talk about what would happen here. If this plum pudding model was correct, if you were to take a sheet of gold made of this plum pudding atoms, right, and you were to shoot tiny little particles at that thing, at that sheet, what would you expect those particles to do when they ran into that sheet? Well, what would happen if you, what happens when you shoot something or throw something down into a puddle of water? It hits that general amalgam mass of water, right? Slows down, but then kind of sinks, but it might spread out a little bit, right? But mostly it's just going to sink. So if the plum pudding model was correct, what he expected was for those particles to pass through that gold foil and hit a detector on the back with kind of maybe a bit of a spread, but mostly just kind of blew up through it. What he found was not that. What he found was that when he shot that, most of them went through with very little dispersion. Almost none of them went directly through. They were deflected in some manner, but some of them were deflected back. You ever thrown a ball at water and watched it bounce off water that wasn't frozen at the time? You say, well, no, I skipped a rock. Like that's angle of inclination. There's a whole method to skipping rocks. But just dropping it. Rocks don't bounce off the surface of water if you just drop them, right? Some of these atoms, some of these particles bounced. What that told us, upon further understanding, was that the plum pudding model was not correct. It wasn't this big amorphous mass. It was mostly empty, because most of these particles went through. They were deflected by certain angles, but most of them just went straight through. Except for a tiny fraction of them that were reflected way off. And from that came our understanding that atoms are composed of a tiny little nucleus and a whole bunch of empty space. It was hypothesized that the electrons were floating in a cloud around that nucleus. Which is pretty much the way we know it works now. There are days when I think I'm like born in the wrong generation. Like, But that's simply because some of the foundational, like some of the really cool foundational experiments, like we're not doing that stuff anymore. Like yes, we are. It's just like next level stuff that you don't hear about because like a lot less of it really impacts your day-to-day life. This really doesn't impact your day-to-day life either, if you think about it, unless you're a chemist. But still, some of these early experiments in chemistry and biology both, even just like figuring out the Planck's constant. You guys know what the Planck's constant is? It's neat. It's a thing. It's math. But Planck's constant, like the guy who figured that out, like that was so cool. We're not doing that anymore because we figured most of those things out already. Not everything. So, from the gold foil experiment, Rutherford determined that we have a nucleus that was positively charged in the center in a big empty region of space that was incapable of deflecting those particles. So that's where we got the structure of an atom from. It was from that, the Rutherford experiments with the deflection of particles. So what is an atom? That center nucleus with protons and neutrons. Protons having a positive charge, neutrons having a neutral, no charge, right? And electrons floating around the outside. Atomic diameter in this case of this particular atom, 10 to the minus 10 meters. That's really small. And out of that 10 to the minus 10 diameter, the vast majority of it is empty space. Because the nucleus itself, 10 to the minus 15 meters. It's kind of neat. That much of you is empty space. There's nothing there other than quantum potential. Conceptually, it's an idea. Your finger, when you touch something, never actually touches it. What do we mean when we say touch? If the electron cloud is simply a big cloud of potential, what would it take for your finger to touch something? The atoms that make up the surface of your finger, the nucleus of the atoms that make up the surface of your finger would have to come in contact with the nucleus of the atoms that make up the surface of the pen, pencil, paper, whatever that you're at. It never does. And yet we are able to sense the pressure. We are able to sense the interaction of those atoms because they are interacting just over a distance. Don't think about that too hard, because it really doesn't matter. But it's just one of those, like, you know, weird things about the reality of reality. How do we know anything to be real? We never actually directly interact. We don't touch. Like, it's this fundamental thing. Touching, holding. You never actually come directly in contact with it. So I suppose that depends on how you define direct contact, though, right? Atomic mass unit. Atomic mass unit is a arbitrary, once again, the deeper you get into this rabbit hole, the more you realize that the way we measure things is completely arbitrary. But as long as we agree on how we're going to measure something, we can all use the same yardstick, then we're good. By the way, so the atomic mass unit, which has a mass equal to 1/12 the mass of a carbon atom. If you like carbon, it's very common. Here's the problem. What's the mass of a carbon atom? Look at the periodic table up there. What is it? There's a 6 and there's a 12.011. The mass of a carbon atom is 12, sort of. But there's also carbon that isn't 12. There's carbon that's 13. And there's also carbon that's 14. So when we do this math, it's an arbitrary number based on our understanding of a very common and therefore benchmark atom. But it's still just arbitrary. So a proton has a mass of 1.0007. A neutron has a mass of 1.0008 atomic mass units. When we're talking about the mass of atoms, we ignore electrons for the most part because they have a mass that is exceptionally small. 0.00055 atomic mass units. Subatomic particles. When we talk about subatomic particles in here, we're talking about protons, neutrons, and electrons. Because those are the things that make up atoms, therefore subatomic, right? These are the Legos that we use to build all atoms, which means all atoms are going to be built with protons, neutrons, and electrons. The number of protons determines which element you are talking about. The number of neutrons determines which isotope you're talking about. And the number of electrons is, under normal states, also just matches the number of protons. So carbon has 6 protons. So how many electrons does it have? 6. If we're talking about a carbon atom. Now most of the carbon atoms you're going to find are going to have either more or less than 6, because all atoms, when they're bonding with other atoms, are attempting to fill that outer shell, so they're going to have maybe 8. But that's because they're sharing with other atoms in order to fill up that outer shell. But a native, normal, neutral, no charge, it's not ionized, naked, if you will, carbon atom is going to have 6 protons in the nucleus and 6 electrons floating around outside of it. We have 2 different numbers showing up on that periodic table. We have atomic mass, atomic number, and the mass number, or atomic mass number. The atomic number is what defines an element. Helium has an atomic number of 1. Lithium has an atomic number of 3. Carbon has an atomic number of 6. What does the atomic number reference? I've told you 12 times already. Number of protons. The atomic mass number is that number beneath the symbol, and that is both protons and neutrons added together. Why is it that so many of these things have multiple decimal places added after them? Well, you could say it's because a proton and neutron don't have exactly 1 atomic mass unit, and you would be correct, partially, but the real reason is because there are things that are isotopes. We change the number of neutrons in the nucleus. We still have the same element, right? But the mass of that nucleus will change. Atomic number is the number of protons, which also therefore equals the number of electrons. It appears above, and in our case to the right, of the atomic symbol on the periodic table. And is the same for all atoms of an element. Because if we change the number of protons, we have changed which element you're talking about. Not to get outside of the box again, but anybody know of the radioactive version of carbon? What is it? Carbon-14. If you look next to carbon on the periodic table, is there something else that also has a total mass of 14? Nitrogen. But the problem is nitrogen, where it does have a mass of 14, we have a problem. We can't just say that carbon-14 is nitrogen, right? Because nitrogen has how many protons? 7. Whereas carbon has only 6, right? But what would happen if you were to say take an atom of nitrogen and expose it in the upper atmosphere to a huge amount of gamma radiation from the sun, and through a somewhat unique but process which happens every day, let's call it bleached one of those protons, and it lost its charge and became a neutron, what would you have instead? What would a nitrogen-14 atom, where one of those protons lost their charge and became a neutron, what would that be after that process? Carbon-14. We would have how many protons now? 6. And what do you call the nucleus with only 6 protons? Carbon. But the problem is that a nucleus with only 6 protons and 8 neutrons is unstable and is thus radioactive. Carbon-14 is one of the only radioactive elements that we are constantly making more of. The sun is literally converting nitrogen into carbon-14 in the upper atmosphere every day. Whereas the amount of uranium-235 on Earth, that is fixed. We haven't found it all yet, but we're not getting more of that, with the exception of, 1 or 2 nifty comets that might, or asteroids that might deposit a little bit here and there.
Carbon-14 is also so measured, that's how you tell age on...
Yes, with recently living things, and that is because during the process of your life, plants will take carbon from the atmosphere and convert it into sugar, right? And then you eat the plant, or you eat something that ate the plant, and so some of that carbon becomes part of you. Moment on the lips, lifetime on the hips. It's one of those things, but it's also real. The carbon in your food becomes the carbon in the molecules that make you. And some of those carbon atoms are carbon-14 atoms. And as long as you are alive, you will continue collecting these carbon-14 atoms. But the moment that you die, you will stop collecting carbon-14 atoms. And they will begin to decay. And if we had done chapter 5, we would understand radioactive decay, and we would know that therefore when they decay, they become something else. And so you can look at something that has been dead within the last 50,000 years, give or take, and you can find out what's the ratio of carbon-14 to the thing it turns into, and you do the math and find out that's about 20,000 years old. But we can't use that to date dinosaurs anymore because we're way too old, yo. Yes, they were collecting carbon-14 when they were alive, but they've been dead for so long that all the carbon-14 has decayed. It is all gone. So we can't use that to date dinosaurs. But we can use it to date, say, things we find from early hominin settlements in North America and argue about whether or not we were here 22,000 years ago, or 24,000 years ago, or 26,000 years ago. And there are some people that just spend a lot of time doing that.
You're saying they date hominids?
Yeah. Hominid human settlements. Like, when did humans get to North America? When did we settle North America? Something wrong with date hominids?
It's so accurate to date, like us today, because of the nuclear testing we also did.
Yeah, there's a spike.
So you know almost exactly how old it is.
Right. Whether or not it was died before or after we began open nuclear testing. Yeah.
50s.
Yep. It's a neat thing. All right. So, atomic numbers and protons. Hydrogen has an atomic number of 1, therefore it has 1 proton. Carbon has 6, therefore it has 6 protons. We've already covered this, right? We know this. Moving on. All atoms of lithium contain 3 protons because that's what makes it lithium. All atoms of carbon have 6 because that's what makes it carbon. Naked atoms are neutral. Now that does not mean that you find these atoms in their naked form, in their elemental naked form, out in nature. But it does mean that when we're talking about an atom of carbon or an atom of hydrogen, it has 1 proton and therefore 1 electron. A neutral atom of calcium, by way of example, has an atomic number of 20. 20 protons, therefore 20 electrons, and has 0 or no net charge. All our positives cancel out all our negatives. Plus 20, minus 20, 0. No charge. This is important. Because most of the things that are useful, used, that make up the biological molecules that make you up are not neutral. They are charged in some way. Which means they have gained or lost what? In order to change the charge away from 0, what do you gain or lose in chemistry? It has to be electrons, because if we change the number of protons, what would we be doing? We'd be changing the element. And that's not what chemistry does. Chemistry does not change elements, but it can change the charge of an element. But the only thing we can do to manipulate that charge is either gaining electrons, which makes it more negative, or loss of electrons, which makes it more positive. right? Once again, that's getting ahead of this chapter. Mass number is the known number of protons plus the number of neutrons. That's the number down below the atomic symbol on the periodic table. Now, the mass number specifically is not what's necessarily shown here. Carbon has a mass of 12.011. But there is never a carbon atom that has a mass of 12.011. Carbon is going to have a mass of either 12, 13, or 14. Because you can't divide protons. You can't have half a proton. You either have it or you don't. You can't have half a neutron. You either have it or you don't. So where does that total number come in? The way that we get that 12.011 under carbon, is there anything new on this slide that I haven't said already? That's number 39, coming number 19. You could do this math, right? If I gave you the atomic number and the mass number or the number of neutrons, and you could, like, just simple subtraction, right? Carbon 12, how many neutrons does it have? Carbon has 6 protons, therefore the other 6 to make 12 has to be neutrons, right? Simple. All of that in a table. Atomic number is protons, mass number is protons and neutrons. Here's a little note down here, because eventually we're going to get to this. Mass number applies only to specific atoms of an element.